So the power rule says the derivative of the nth power of x is n times x to the n minus 1th power. So to prove this, let's do it with the definition. We're going to let f of x be x to the power n, where I'm going to prove this only in the case where n is a positive integer, okay? So 1, 2, 3, and so on. It works more generally, but this proof is only going to work when n is a positive integer. If you wanted to prove it for other values, you'd have to do something else. But let's do it for the positive integer case at least. We end up using that case a lot, but like I said, it's true more generally. So here we go. Let's take the derivative. F prime of x, which as always is the limit as h approaches 0, f of x plus h minus f of x over h. So what's this going to be? The limit as h approaches 0 of, well, f of x is x to the n, so f of anything is anything to the n, f of x plus h to the n. And f of x is just x to the n over h. Okay, so in order to continue from here, I'm going to need to expand this out. And I'm going to use something called the binomial theorem. So the binomial theorem, it tells you how to expand out a binomial. The binomial being something plus something else, all to some power. So power of a binomial, I guess. A binomial is just, something with two terms. So in this case, the two terms are x and h. And the binomial theorem tells you how to expand out a power of a binomial. So it says that if you do x plus h to the n and you expand it out, what you're going to get is x to the n plus n times x to the n minus 1 times h plus n choose 2. This fancy number is called a binomial coefficient. If you want to know what it is, look up the binomial theorem. Then the powers on x go down and the powers of h go up, plus blah, 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 plus. It goes on through as all the powers of x go down and the powers of h go up, you eventually get to n choose n minus 1 times x to the power of, this would just be 1, right? H to the n minus 1, and then finally the last term is h to the power n. Yeah, this binomial theorem is really interesting and very useful in lots of situations. So these numbers, 1, n, n choose 2, then it'd be n choose 3, n choose 4, all the way up to n choose n minus 1, finally the last one, 1. These numbers, these coefficients, called binomial coefficients, they are the numbers that actually appear in this neat thing called Pascal's triangle. So this is this triangle of numbers that you build by taking each row. You start the next row below with a 1 on the left, and then in between each two numbers on the row above, you write their sum, and you end with a 1 on the right. So put a 1 on the left, 1 plus 2 is 3, 2 plus 1 is 3, put a 1 on the right. Put a 1 on the left, 1 plus 3 is 4, 3 plus 3 is 6, 3 plus 1 is 4, so on. This is called Pascal's triangle. And the thing we're going to need to know from Pascal's triangle, from the binomial theorem, is that these numbers actually, it's not important if you don't know what these numbers are. They're just some numbers, these things, that appear in Pascal's triangle. But the thing we're going to need to know is that when you expand this out, these numbers, which are given by the numbers I get when I go across the rows in Pascal's triangle, they always start with 1, and then the next one is in n, where n is this power of a binomial. So for example, if I expand out x plus h to the power 4, then actually I'm going to get the numbers in this row right here. If I wanted to do x plus h to the power 5, I'd have to make the next row. But these numbers, they tell me when I expand out x plus h to the 4, I get x to the 4 plus 4 x to the 3 times h plus 6 x squared h squared plus 4 x h cubed plus 1 times h to the 4. So you can write out these expansions really efficiently with this nice trick, the binomial theorem. And the binomial theorem says the expansion looks like this, where these numbers, as I go across, are the numbers that appear in Pascal's triangle. All right, so knowing that, we're going to expand this out. So I'm going to replace this x plus h to the n with this expression right here. But I guess I'm not going to write this term. So I'll write the first maybe 3 terms and then the last one. So maybe I won't write this one, just to save space on my piece of paper. Of course, there's lots more terms in here, right, that I could write. So here we go. Let's expand this out. So now we have the limit as h approaches 0. What did this expansion look like? I'm going to need a lot of room here. X to the n times x to the n minus 1 times h plus, the next one was n choose 2, x to the n minus 2h squared plus blah blah blah, and the last term of the expansion is h to the power of n. So there's a whole bunch of terms in here. Turns out it's not going to be important what they are. You'll see why in a second. And then I have the minus x to the n hanging out. Let's just check. I just expanded this out, and then I still have the minus x to the n, right? So I expanded all this out, minus x to the n over h. Okay, so what are we going to do with all this? Well, there's an x to the n here and a minus x to the n here, so those add up to 0. So those are gone. And with what's left over, you can see, start to write these out, choose 2, x to the n minus 2h squared, all the way up to h to the power n h. Now the important thing to notice is that every term in here has an h in it, and the powers of h are decreasing. So this term has h to the power 1, this term has h to the power 2, the next one would have h to the power 3, h to the power 4, and so on, all the way up to h to the power n. So h is a common factor in the numerator. So we're going to factor it out. Now I've got h, n, x to the n minus 1. This n choose 2 is still here. X to the n minus 2 times h, because it used to be an h squared, and I factored out an h. And then the last one, h to the n minus 1, because it used to be an h to the n, and I factored out h. Now these h's will cancel out. And what are we left with? All this stuff without the h. Oh, sorry. Whoops. That is definitely not an h. That should be an n. And choose 2. X to the n minus 2 is h plus blah, 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 all the way up to h to the n minus 1. Oh, and this h canceled out, so I just have 1 now in the denominator. Great. And now, look at this. This limit is not indeterminate anymore. The denominator is 1. It used to be 0 over 0, but now the denominator is 1. So now as h approaches 0, let's look at what happens. All of these terms, the terms that used to be, the one that started with n choose 2, all the way to the end of the expansion, all these terms, they all have h in them. This one is h to the power 1, the next one would have h to the power 2, h to the power 3, h to the power 4, all the way up to h to the n minus 1. So as h goes to 0, all those terms go to 0, because they all have h in them. So each of these terms, they all go to 0. Everything in there goes to 0, that one goes to 0. So the only thing you're left with is the n times x to the n minus 1 on top, and the 1 on the bottom. So therefore, this limit just gives you n times x to the n minus 1. And that's it. We took the derivative of x to the power n, expanded it out, we wrote it down, did the expansion. These things added up to 0, factored out an h which cancelled. Now all the other terms have h, except for the first one. So the only thing left when h approaches 0 is the first term, n x to the n minus 1, and that's it. That's the derivative of x to the power n.